The topic will be virtual work. Virtual work for reactions. In fact, because this virtual work concept can be applied to calculate some other things too. That's why on this course we more concerned at the moment, we more concerned with reactions. So we adopt this method to do it. Now, this one has two words, but a topic. Okay, one is virtual, one is work. Work is the work that you already study in high school in mechanics, okay, in physics, sorry. Then we will talk about it later. The word virtual, like, usually means something that seems real but not quite real. Okay, in Thai it's called เสมือน right? Okay, let's talk about topic today. Okay, because it's such a very strange name. So we first will discuss about what it means actually, which is gonna make you even more confused, I hope. Then we talk about the work done. How do we calculate work done? Okay, because at the moment we're looking at three different things, three different applied forces. One point load, which we usually call force. One angular force, moment, or sometimes we call couple. And then we talk about distributed load. Okay. But this one here has to be a little bit simplified, so we will not talk about ununiform, non-uniform. We just talk only uniformly distributed load, meaning it's always equal in this topic. Okay? The reason is because it makes our life easier. If it actually not uniform, then you probably have to integrate most of the time. Okay? Then we talk about types of the virtual work and which type we actually calculate here. Okay? And then we'll see, we have to prove a little bit more on the virtual work done on a system in equilibrium. What is the value of the total work done? Then move on, we'll see some examples. And of course, hopefully we actually run on the right time. Therefore, in the second hour, I hope you have some experience of it before we actually leave you in the abyss. Okay, let's go. Definition. I'm not joking. Okay? Definition, because the word virtual means almost real. Look like real, but not real, right? So it's actually, the virtual work means it is actually similar to the concept of work done. Okay? But it's not really work. It's just virtual. Okay? Imagine this, right? You are actually in a lecture room. Dr. Goran teaching Fortran, right? You were searching internet, you were playing games, right? And then Dr. Goran walked in front of you, you switch the screen, whoop, it's Fortran coming up. That is virtual work. Something that looks like you are working, but you are not really working. You get the idea, right? So, let's see how it means. But before we can go to that, as the topic layout, since this is going to be very similar to work done, so the way we calculate it probably similar to it, to the work done. Okay? So let's study what is the real work. If you don't know what real work is, then you can't pretend that you are working, can you? Right? So let's study what real work is first. Start from work done by a force. A force applied, F. Then a box move. To the right hand side maybe, to the distance of delta. Meaning at first it's here. The force push it come here. What is the work done? F times delta, right? That one, the work done is simply calculated by F multiplied by delta. Now, notice this is not moment. So this delta and this force is not 90 degrees. Is there any rule about it? Let me change the scenario a little bit. Okay? The same box, the same force, but this time from some magical reason, the box doesn't move to the right hand side. The box actually moves downwards. Distance, delta, the same distance. What is the amount of work done here? 0. So what's the rule? Let me change the scenario a little bit more. The same box still, right? This time for, again, magical reason, it doesn't just move to the right hand side. There's only one force acting. Let's say there's no weight, right? Just force, F. When it moves, it actually moves this way, right? So if it moves downwards this way here and to the right hand side, let's say it's angle theta. That angle theta is the distance of the vector distance and the force. So that side will be delta cosine, right? Downwards here, delta sine, right? What is the work done? F times U, or F times delta, or F times delta cosine, or is it F times sine, F times delta sine? Which one? So what's the rule? It has to be on the same line, right? Meaning, if the force and the distance is on different line, then you have to take component to be on the same line only. Okay? The same, you can actually take the component of the force into the delta line, right? But because that angle, that's the force will be that line, take that F cosine theta. It will be the same equation, right? Basically, F cosine theta delta or F delta cosine theta, the same equation. Okay? Which means, if the force pushing to the right, but somehow the box moving to the left, then the work done will be negative, because the cosine 180 is minus 1. Okay? Usually logical meaning, you try to push the box to the right hand side, it moves against your attempt. So you lose work, not you get work. Okay? So that's the idea. So let's summarize for the work what the force done. Okay? What about the moment? We have a couple. At the moment, we don't have any clue apart from that the work done is calculated by a point load time distance. That distance and that point load has to go on the same line, right? So we have a moment, we don't know what to do with it. However, we realize one thing. That moment can be described by a couple, two forces equal and opposite, right? So if we actually try to change it into this picture instead, right? Remember, the moment will equal to the force times the distance. Now, before we move on, notice that, look at the right hand side box. No matter how you move the box as a line, there will be no work done, because you have plus F and minus F cancel each other all the time, right? So just moving left, right, up, down doesn't have any work done. The combination will be 0, okay? Therefore, the only way we can study this is to rotate it, okay? So let's get rid of that box first. Let's say this box is rotating about a point O, okay? Some certain distance. We don't really care, okay, where the point O is the same. Now notice that is, once it rotates, this is the original line from point O to that point and that point. Then once it rotates, from black line, the whole body rotates into the blue line. Okay? So basically, we can say that F actually moves this distance, and that F moving that distance bigger. Okay? The distance between F actually defined by that equation from the beginning. Point O, let's say it at distance of x. It could be any x. It could be longer, it could be shorter, it could be between the force, it could be the right hand side. It's arbitrary. In the end, it will be not used. Okay? But anyway, therefore, to calculate, to study the total work done by this system, we identify that distance as delta 1. That is that force moving, right? Then that is delta 2, which is the other force moving. Okay? Now if we rotate it, well, let's just talk about the work done first. Okay? Then the total work done would be the work from this force combined with the work from this force. Correct? Therefore, now notice that this F going that way, but when you rotate this way from black to blue, meaning delta coming from the black line to the blue line. The force going that way, delta going that way, negative, opposite direction, right? We just discussed. However, that force moving downwards, the object, the point also moving from black line to blue line, the same distance, the same direction. The work done therefore positive, F times delta 2. Okay? So that's the total work done by these two forces, which equal to the moment, of course. Now, notice that that two belonging to the movement in a circle, a small arc, a small curvature, belong to the same center. Okay? Meaning we can calculate the arc length. Let's call that angle theta, the one we rotate. Okay? Then delta 1 will equal to x times theta. Where does it come from? The arc length is equal to the radius times the internal angle. Are you familiar with that? The radian unit, the radian number, actually is comparison between the arc length and the radius. Okay? You know why when you calculate the whole circular, the parameter of a circle, what is called circumference of a circle, you use 2 pi r, correct? It is the same equation. The 2 pi is because theta going the whole circle, right? Theta is 2 pi. Okay? It is the same equation. In this case, it means that if we're going to apply that, delta 1 is equal to x times theta, automatically theta unit will be radian. Okay? Cannot be degrees. It has to be radian because of this relationship we are using. And of course, delta 2 will equal to the whole distance, which is x plus d times theta, right? Substitute into the equation. That is delta 1 theta times x, delta 1. Delta 2, the whole distance, x plus d times theta, right? Now, notice that when you expand the term, that term will be plus f theta x, right? Which cancel out with that one. The second term will be only f theta d, which is that term there, right? Now, because we haven't actually deleted yet, it's easy to quote that f times d is in fact moment, the original moment we are talking about. Okay? Therefore, the total work will be equal to the moment times theta. Notice that this work done is positive because the moment rotation and the body rotation is on the same direction. If it go against one another, that work will be also negative. Okay? So, if it's a point load, it is a distance that counts. Okay? If it's moment, then the rotation that counts. Questions? Wow. No questions. Okay. Cool. The next one, well, as I said, we learned about three types of forces at the moment. So the next one will be, what about work done by distributed load? This time here, again I emphasize myself, is only when it's uniform. If it's not uniform, please integrate again. Okay? Are we clear? This distributed load has to be equal. It cannot be triangle, it cannot be parabola, it has to be like rectangle box, right? Only. So, there we are. Let's say there's a member, right? Okay? That member is supplied the distributed load equally, magnitude W. It could be 10 kilonewton per meter, it could be 50 kilonewton per meter, it has to be the same. It applies only from A to B, nowhere else. Okay? Then, of course, with the work done, you have to move the body. Right? It's about force and motion. Thank you. Okay, so let's move that line, right? That's general pace, then it moves like that. Okay, it could move as a curvature, it could move like parabolic or sine curve, sine wave, I don't care. Okay, it's just hard to draw, so I just draw a straight line. Okay, let's say that we know it. We can actually describe this distance from here, from point A start here, drop here. Point B from here, drop here. And on the delta, we could actually describe it as a function of x. Notice I actually indicate direction of x. It doesn't matter where it starts. Okay? Now, so notice that at that point, then I pick a small element, the red element, because it's changing. I need integration per se, right? So I design a small element there. The force and the delta is defined on the same line. Okay, so we don't have to take the angle. If it's not, then take the cosine side into the same line first. Okay, then that small strip, of course, will be the full height of W. The width will be dx as usual. Okay, so what happened is I will calculate what actually is the force in here and how much work done by it, and then I sum them all up by integration from A to B, basically. Okay. So the small force in here, remember how we calculate the distributed load. The total force is equal to the area or the picture, right? The height of the area, that red area is rectangle. It might be an angle, but it's still rectangle, right? So the height times the base. The height is W. The height here, W. The width, dx, right? So the total force is dF. And of course, to make the work done by that small element, that force at first begin here. When it moves down here, right? So the total work done is the delta times the force dF we just talked about. Okay? And of course, force is W dx, we just discussed it as well. So the next is, of course, substitute into the equation. Now, if we want the whole term, the whole thing, what do? Then we integrate from A to B, correct? Not before A because there's no load there. Okay, not after B, no load there either. Okay, only where the load exists from A to B. There we are. Now, notice that in those terms, delta we described already as a function of x. This integration is with the x, so we cannot leave it out. It has to be in there. However, W, I emphasize again, it is uniformly distributed load, meaning W will be constant throughout the whole A to B, right? If it's constant, then I can take it out of the integration. Okay? Now, that integration, although in a very unfamiliar form, it is actually the same thing as integration of y dx. Basically, you integrate the function with respect to the variable. So what you get is in fact the area under the graph. And of course, what area are we talking about? Okay, that area. What area? Area under the graph. Then this is not area of the load, because this is area of delta. Correct? Therefore, that area has to be here, under here, there, like that. Okay? So, if that area is in the shape we can calculate, then it will be quite simple. Just calculate the area and then time time W, whatever the magnitude is. If it go together, then positive. If it go against one another, again negative, of course. Okay? Questions? Huh? Which part? Huh? If it goes on the same way, that one, or W coming downwards and the right? So that small df will have to go this way, right? Therefore, delta that way become positive. Imagine if delta go that way, that form will be negative, and then you integrate everything become negative as well, right? So if the delta, the area is on the same direction as the as a distributed load is positive. It is against one another, it is negative. Theory is not difficult. When we play around with the support, that is headache. Okay? That's it. 3 equations that we need to know. Oh, no. We still need one more, but it will come. Okay, let's talk about what kind of virtual work we have. The word virtual work is, as I said, not real work. Something similar to it, but it's not, right? We pretend work. So basically, we have one type, that is, we use real force and what we call virtual displacement. Okay, or well, imaginary per se. Okay, or if it's real movement, then we have virtual rotation. With this technique, we never find out what is the fake values. We always find out the real thing. Okay, so in this system of thought, then we try to find real force and real moment. In this case, would be reactions. Okay, the other type that you will not learn until another year later. Okay, in structural analysis 1, I think. It is actually virtual force, real displacement, virtual moment with real rotation. Again, we don't find what is fake, we find what is real. So when you apply this technique, it will be real displacement and real rotation to be found. Okay? So, before we can apply it, then because at the moment we know how to calculate the work, but we don't know what is the relationship within the system. Right? So the next one, because we are talking about equilibrium, we are talking about virtual work within the equilibrium system. Let's say there are so many forces acting on this body, there's no rotation. Okay, if it lacks rotation, we can consider with the moment later. Okay, now let's say it moves. That one there, notice star. The star in front designates that it is not real, it is virtual. Okay, so we imagine it move. It doesn't really move. Okay, just pretend it moves. Now, if we try to calculate, notice the name. Okay, these are not 4 forces. That F1, F2, F3, blah blah and blah blah until Fn. Okay, so there could be millions of forces. We don't care. Okay, symbolically we need only 4. Otherwise we have to write down million numbers. Not very nice. Well, never mind. Now, notice that these forces, no matter how you calculate it, you have to take the component onto the same line as delta first. Correct? Remember the rule? If it's 90 degrees, it's 0. So it's only on the same line. So when we calculate it, then we will take that into the component that we call F1 delta, meaning we take component here, F1 delta, and the other one going that way. Okay? It's almost like F1x. But this is not x-axis, the axis of delta. Are we clear? So, can I call an axis Kokai? If I say F1x, what do I mean? I have F1 here. What do I mean by F1x? It means that it should be in that line. What do I mean by F1y then? F1y is in that line, right? Vertical. F1 delta meaning because delta is in this line, F1 is in that line, I take component into the delta line. Okay? Is that clearer? So, then I will take all the components into delta line. F2 we will take that component, not the 2F2, that component here. Okay? F3 will be that component there, which we call F3 delta. Okay? And each of the force will have to time delta to be work done. Correct? So, that is the expression for it. I have a body, right? Then I have force here. Say, let's call it F1. Okay? However, the body doesn't move that way. The body moves that way. Right? Delta or delta star. That's called theta. Then I will take component, 2 component, correct? Into that one F1 sine theta, then that one F1 cosine theta, correct? Compared to this case, we have X, we have F1 theta, right? Then I take two components, that one will be F1 cosine theta, that one we call F1 sine theta, right? That one is called F1x, correct? So why can't I call that F1 delta? Oops, sorry, F1 delta, because it's on the line of delta. It's just I call that axis delta rather than xy, that's all. Okay? Are we clearer? Okay. Then the force done by that F will equal to the U1, then equal to F1 delta star, correct? Right? We agree? Yeah. So metaphor into that one, oh sorry, that is the same. Meaning, I would take F1 into that line, which I call F1 delta, right? And then for the work, because it moved delta star, therefore it becomes delta 1 times delta star. The same explanation go on until the end. Okay? Now, the next step. The idea is this. Although this delta is imaginary, although this delta we don't assume big number, it is not zero. So if it's not zero, it means that I can actually take it out as a factor, right? Because every term has delta, right? Therefore, I could say that the work done, I take delta star out, and the inside I have just the force. Okay? Notice that that force is on the same line. Although force, as we discussed, is on the line of delta. We argue that in this system, in this system, the body is in equilibrium. If the body is in equilibrium, it means that all this summation of force must be zero, right? If summation of force is zero, then it doesn't matter what delta star is, the total work done must be zero. Okay, I repeat myself, delta star is assume a value, an imaginary value, we don't know what it is, but it's not zero. Okay, so to prove the work done zero is actually come through sigma f delta is zero because of the equilibrium, right? Equilibrium said no matter which line you take, the summation of force on that line must be zero, which we usually call sigma fx 0, sigma fy 0, and sigma fz 0, right? So as long as you sum every force on the same line, it must be always zero. Otherwise you create acceleration, right? We clear here? Let's move on. What about if it's a moment? Again, a situation similarly, a body having so many moments apply on it. M1, M2, M3, blah, blah, and blah, blah, until M4, or sorry, until Mn, right? Then the body rotates certain amount, theta. In this case, again, it's word imaginary, so it is theta star, okay? Then, again, the same summation, the total work done inside the system. Then, M1 times theta, okay? Negative, when you really calculate, put in number, then it should be negative. This one is just symbolic, okay? Then everything times M1 times theta, and then combine all of them in terms of work. Again, because theta star, although small, it is not zero. Theta star, although imaginary, it is not zero. Therefore, we can take it out as a factor. And there we are. Now notice that inside the bracket here is actually M1 plus M2 plus M3 until Mn, meaning it is a summation of all moment on that body, correct? Which we usually use symbol of sigma m. Again, if this body is in equilibrium, sigma moment also has to be 0. And therefore, the work done is 0. Okay? What does this proof mean? It means that if the body is in equilibrium, a force will make the summation of all work done by the force is 0. The summation of all moment done is also 0. So it means that when you combine all of them in the body, it must also be 0. Okay? Funny enough. So in the end, we're going to use that. But a little problem is that we have only one equation, meaning we can see only one unknown. If we actually use free body diagram, we're going to end up with at least 3 unknowns, right? So what we use is not really free body diagram, but we will see it. Don't worry about it. Okay, so at least the summary of the virtual work done on an equilibrium system is that everything is 0. Okay? Now, as I said, we have only one unknown. Okay? This step here might not make much sense to you yet, but I hope it makes more sense when we try it. Okay? The idea is that we want to see one reaction at a time. Okay? Now, to see one reaction, the only way is we actually release the constraint first. Okay? Sometimes some certain support have 2 reactions, some have 3, right? Some have only 1. We only release the one we want to see first. Okay? We will discuss in detail later what it means. Okay? But the first concept is that we actually release the constraint. The constraint that allows us to actually see the reaction we want to find. That's why it said relevant constraint. Okay? Not any constraint, but the constraint that we know that relate to our reactions. Okay? Then, once you release the constraint, it is not the same question of the picture anymore. Right? Because we release one constraint, one reaction is missing. So we apply one reaction back, the one we want, so that it becomes equivalent to the old system. Okay? Now, for us to start calculating, we have to imagine that this force do some work, or this reaction do some work, so that it can appear on our equation, the virtual work equation. Okay? So we start moving it. Okay? Again, this is not real motion. This is imagined in our head, right? Well, in the end, it will be on drawing on the paper. But that's why it comes from the word virtual displacement, because it's not real. We just imagine it up. Okay? So once we move it, then we apply the sigma u star equals 0, and then theoretically we should get the answer. Okay? Let's see. Oh, I just make the red because it's the keyword of each step. The first step is release constraint. Second step, add back the reaction, right? And then the next step, move is in such a way that reaction work. You can see only one reaction at a time. If you see 2 reactions, you're in trouble, because we have only one equation. So one reaction at a time. Okay? Then move on here. Just a beam. Okay? Distributed load moment, 1 pin support, 1 roller support. We know it already. Okay? Just to narrow down the scope. In this case, we don't find all reaction. Just for example, what I want is vertical reaction at point A and point B. Okay? You ready? Steady? Okay, let's start from, don't forget, we can see only one reaction at a time. We want to find two reactions. We have to choose which one first. Okay? So this one I choose R1Y first, RBY first. RB is on the roller. Okay? Now, the first step is I have to release the constraint at point B then. There is only one constraint at point B, right? The constraint is that it cannot move up, down, right? Release the constraint is almost like I move out the support, right? Now, notice that picture is never equivalent to our questions, right? Because this picture, our question have RAX, RAY, right? And RBY. This picture, we have RAX, we have RAY, but we don't have RBY, right? Because there's no support there, right? So what we do? We supply RBY back into it, so it becomes equivalent again there. Just add it in, right? So now, if you check, then at point A, we have RAX, we have RAY. At point B, we have RBY. So it's the same now, equivalent now in our force system, right? So next, we want that RBY to work. If it doesn't make any work, if it stays still, then sigma U star is always 0 because RBY times 0, it disappears. So we have to move. So if I move point B up, what happened? Notice that point C can move freely, right? Point A cannot move, cannot go up, cannot go down, but can rotate. So if I push point B up, the whole body will rotate about point A, correct? So the picture I have should look like this. From the black, then I move point B upwards, then it rotate that way, right? Because that point stay. Okay? Before we start calculating, maybe I name them first. Okay? Let's call that delta B star, delta C star. That is a moment, right? Therefore, I need theta. Okay? That moment is applied at point C, so I want theta C star. Okay? Just a name. Now, once we name them, then we could then calculate the work done of the system. Okay? Because we have this equation here, sigma U star equal to 0. Okay? At this point, no force, ignore it. Okay? That force pushing upwards, the name of the force is RBY, right? The distance it moves is delta B star. From black to blue, it moves up, the force also up, so it is positive. Correct? Now, the distributed load, this whole distributed load is magnitude is 30. How do we calculate it? Do you remember? It is the magnitude of the distributed load, W, times the area of the displacement shape, right? That is the magnitude, W. The area of displacement shape, then the black upward here, and then the blue, triangle. Correct? That angle, if we move just small amount, that angle is about 90 degrees. Okay? This movement is actually small. We just draw it big so that we can see it. Okay? Therefore, the total area will be a half times the height and the base. Right? A half, the height is delta C star, the base is 5. Right? Now notice that the work done going down, the distributed load going down, displacement going up. Therefore, it's against one another. Therefore, that one is negative. Okay? Then point C is rotated by theta star, theta C star. The moment is 120, theta C star. Notice the moment is clockwise. The theta is anti-clockwise. Against one another, therefore negative again. Okay? Therefore become negative. Now at the moment it seems like we got stuck with 3 variables, 4 including RBY. However, these delta stars and theta stars are linked by geometry. Meaning, I could use any technique I want, maybe similar triangles or whatever I want to actually relate them. In this case, I will relate them by theta C star. Because I know that if that angle is theta C star, that angle is also theta C star. Correct? Using the radian relationship, then I can say delta B is equal to 3 times theta C star. And delta C here, delta C is equal to 5 times the angle theta C star. Correct? And then I substitute into that equation we already have. Notice now that we have our term theta C stars. In this case, it means I can again take the factor. Cumulatively, again, I can say that, and I already say it, theta star is not zero. It is small, but it's not zero. If it's not zero, then inside the bracket, when you put theta C star out, inside the bracket has to be zero to make that equation true. Correct? In other words, I will have that system inside the theta star, and then I can calculate RBY. Okay? Then, what is unit of RBY? Kilonewton. Okay? Notice that unit there. Okay? That one is kilonewton. That one is a factor. That one is, that's kilonewton per meter, force per length. Okay? That delta will be length, right? Delta is length. Phi is also length. Correct? So that total unit is force times length. Okay? That moment, that is the moment. Unit is kilonewton times force times length already. Right? In this case, kilonewton times meter. There. Theta, as I said, in this case is radian. Radian doesn't have unit. Unit is 1. Okay, so that term is also kilonewton meter. That delta is length, in this case meter. Therefore, RBY must be, as you said correctly, kilonewton. Positive means we assume the right direction again. The rest is the detailed calculation. Now, one thing about this technique is that once you finish the calculation, the picture is not reused. I understand myself, it's not reused. You throw it away. Okay? Meaning, for the next step, when I want to find RAY, I will start again from the original picture, a pin and a roller. Okay? This time I want to say RAY, not RBY. Therefore, the roller at B will stay. Okay? However, I will release it, that one. Notice that I did not take the pin out, because if I take the pin support out, I will see RAX and RAY at the same time. I only want to see RAY, meaning I want something to represent RAX, right? Meaning only one reaction I want to be representing. That would be, of course, the roller support, right? So in this case, that roller support will supply my RAX, that one will support my RBY. Okay? So now the only one reaction missing here is RAY. Right? To make it equivalent again, then I add RAY back into it. There. Okay? Once I apply RAY back into it, then I want to move point A. Notice RAY is up. Or down. Then delta point A should be moved up or down as well, so that RAY works. Well, by the way, by the support, you cannot move RA out anyway, right? Because the roller support said you cannot move away from the support, right? So if I move RAY up per se, notice now the different from last time. Because what stopped my motion doesn't happen at point C. Right? Point C, there is no support at point C, meaning point C can move up now freely. However, roller support at point B said point B cannot be lifted up or cannot be sink down. Point B has to stay there. Correct? So the only way I can move point A upwards, right? This is point B, right? This is point A. If point B cannot move up down, the only way I can move point A upward is this way, right? So like the leverage system in this case, if I want to move point A downwards, it will be that picture, right? Basically, what stop motion is at point B, not point C, okay? So that is the picture. Once we get the picture, then we name the delta we're going to use, okay? And theta we're going to use. Then we again put in that equation. Notice this time, because the movement make the distributed load two sides. The left hand side of B, the displacement go up, the force come down. The right hand side, the force come down, displacement come down. So the left hand side, the work done negative, the right hand side, work done positive, right? So the easiest way is split into two of them, right? That one represents that triangle, where the displacement is up, the force is down, therefore it's negative, okay? That represents that triangle, where the force is down, displacement is down, therefore positive, okay? The moment 120 going clockwise, rotation from that line to that line clockwise as well. So this time positive. Then using triangle again in any system you like. In this case, I still change everything into theta C. Okay? You can link it back to delta, one of the delta. That is also fine. It's just a ratio. In the end, you end up the same answer, right? Again, every term have theta C. Accumulatively, if theta C is not zero, then we can work out RAY. In this case, we get minus. What does minus mean? It means we assume the opposite direction, meaning actually it is downwards. Okay? And the system go on this way. Summary. Let's look at one more example before I let you have a break. So when you come back, you can try it. It's a little bit more complex system this time. This time we have a fixed support on the left hand side, we have a pin joint, and then we have a roller support at point C. What the question asks here is and this is the reason why they develop this technique. Okay? Because at the moment it seems that you have to do more work than the normal free body diagram, right? So why do we do it? This is the reason. If I want to find, for some reason, I only want to find moment reaction at point A and vertical reaction at point A. Thinking about equilibrium system, you have to take about 3 equations on the right hand side first, right? And then apply maybe 3 more equations on the left hand side. In all 6 equations to get the answer. If you have more sections, then 3 more equations, of course. With this virtual work technique, you need 1 equation. This is how it goes. Let's start from moment at point A. Right? The first step, from fixed support, I want to see moment at point A, then I want to high RAX, RAY, but I want not to high moment anymore. Then you have to ask yourself, what support gives you RAX, RAY? That is called pin support, correct? Therefore, you change the fixed support at point A into the pin support instead. Again, the same argument. We are not the same. They are not equivalent. So we put the moment back in. Now the force system is equivalent again. Then we move in a way that moment work. How does moment work? Moment doesn't work with up, down, left, right. Moment work with theta, rotation, correct? So we want to rotate member AB. Okay? Then, if we rotate it, it may be looking that way. This way I rotate it clockwise, right? Notice that the support connection has to be obeyed. Shh. There is no support here, just connection. Right? Meaning it can go up, down, but it cannot separate the two sides. It can rotate freely. However, point C has to stay. right? So basically, if you move that one down, rotate that one clockwise, point B will move down, right? Then, to make sure that point C go back to the same place, then it has to go back up that way. Okay? Now, since we already know how to calculate the work done, right? We give the name to the point that we need, then we put into equations. In this case, only two of them. The moment is self-distributed load, right? From 6 equations, you need only 2 equations to do it. Okay? Again, you have about 4 sections, you probably need 12 equations. With this one, you need 2. One is the work done equation, the other one is the geometry relation between delta and theta. Any question with this picture? Because it will get more confusing very soon. Okay, the same concept. Once we finish calculation, we throw it away. Okay? Now we want to find RAY, we again start from the original picture. If I want to find RAY, meaning I don't want to see RAX, don't want to see moment. We have a support that has one reaction and one moment, right? The symbol is that one there. One reaction 90 degrees to that, in this case, wall, right? And then a moment, meaning RAX is hidden inside the support, moment is in the support. What we are missing here is RAY. So what we do is apply RAY back into it. How does RAY work? It is only when it moves up or down, correct? So we're going to move point A up or down. In this case, up. There, become blue line. Notice the condition. The condition at point A at the moment said it cannot go away from the support. It has to stay there, right? The other condition said it cannot rotate. So when you move up, the line is here. If you move up that way, it rotates. Correct? So the only way you can move it up without rotation, meaning it has to lift up as a continuous line like that. The whole beam will have to be lifted up at the same level. Correct? Lift up like this, rotate. Lift up like that, rotate. It has to be that way only, not rotation at point A. Correct? Okay? So once you move it, please check your support condition. Okay? Then it moves a straight line until now. Suddenly it hit a pin joint here. Oh, I forgot to draw it, sorry. There's a pin joint here, right? In the question. Therefore, at this point, pin joint, then it can go back down to point C. Again, point C said cannot move up, down, right? Correct? Now notice that, again, we only need 2 equations here. Oh, even one, I think, this one. There. Because that blue line here, the displacement shape here is trapezoid. See, pink chin, if there's such a word, right? Okay, therefore, there. And because delta is the same delta already, then, thank you, then we can straight away take it out. Oh, piece of cake. I hope you bring your support, because I actually posted that you should bring it today. The sheet of your support, right? Because you will need it to check the condition. Okay? I think we deserve a break. Yep. Okay then. I see you guys in 10 minutes. Time is nearly up. I'm happy to inform you that this is going to be the last class before midterm. Okay? So let's revise a little bit of what we have done so far. Okay? We open up Should I just try the, maybe I go back to my throat challenging system. Okay? When we open up the first in our course, we talk about the force couple system, right? That is the main topic, the force couple system. Okay? AKA resultant force and moment, right? Whatever you want to call it, resultant. Okay? That's the first concept on how we actually consider forces and moments and how we combine them and subtract them. Okay? And we briefly go into general equilibrium, talking about contact surface, talking about rolls, right? Just a little bit. Then we find more pressing issue on how to find where the point, where the load is, which brings us to the centroid. From centroid, we realize something that we have to deal with is the most favorite topic of we saw, the area moment, the moment area, the area moment of inertia. After 3 horrible, confusing lectures and questions, then we come back to our engineering equilibrium. Okay. Then we do nothing, just sigma f, x, sigma f by sigma moment, so boring, right? So we move on to today, the virtual world. More exciting, right? More challenging. It's almost like a fluke, right? It's like a fable tales. It's like, you know, fairy tales. I don't know why 6 topics, right? 1, 2, 3, 4, 5, 6. Oh, it's that if we plan it ahead, right? But you can guess. Currently, if they're not changing my exam paper, or I don't decide later on, but if I decide to change it, it will be less, not more. Okay? If they want to change my exam paper, it tends to become easier, not harder. Okay? At the moment, there will be 6 questions. Unequal marks. Okay? In each question, there will be A and B. Point 1, point 2. No more than that. Okay? The first part, A, or point 1, whatever you call it, will be dealing with concept or theory or proof. This will include assigned reading. Okay? Then B will be hardcore mathematics, meaning you have to calculate with the answers. This one might involve integration in some kind of, as I said, some kind of concept, some kind of proof. This one more is application, basically. Okay? In each part, that one will range from 1/3 to maybe about 40 degrees, 40%, sorry. So that one ranging between 60% to 2/3, depending on the question. It will be a little bit more than usual. The exam paper this year will not be the same as the year before, because we have the area moment adding in. The good thing about it, the best thing about it, is that you have to understand. It means that you have to be able to prove. The good thing about it is that the question I ask will be similar than the year before. because you don't have as much time. The word is simpler, not simple. Okay? So don't misquote me, please. The word is simpler, but it's not by no means simple per se. Okay? Any questions? Oh, by the way, on March the 10th, okay, which is Tuesday after the exam, please be on your best behavior because there will be some guests from Vietnam come to observe our class. Okay? They will be staying in the back. So when you see me weak, it means that you have to be quiet, so attentive. No, just be natural. Just let you know beforehand that if there's some noise behind in the back, don't be so scared. That's maybe our guests coming in to observe the class. Okay? Any questions?